Hi everybody. I'm going to be talking about KPRA's a KATO dual modality mammography system. So BMEC forms part of a Cape Town-based team of about 10 electronics, software and mechanical engineers who have been developing the system over the past 7 years. So shown here is the KATO system. Its main components are a tube which generates X-rays, and it sits in this region over here. The X-rays are detected by an X-ray sensor which sits in this box, and that's called the breast platform. During a mammogram, a woman's breast is compressed between the compression paddle, which is this clear plastic thing, and the breast platform. What makes a KATO special is that in addition to the X-ray detector, there's also an ultrasound probe in the breast platform. And the addition of ultrasound to X-ray has been shown to improve breast cancer detection. And improved detection leads to early treatment, which can save lives. So the focus of this presentation is on a KATO's ultrasound development and the challenges we faced and overcame during that development. We won't talk much about a KATO's other systems. This is a close-up of the breast platform. This is a fake breast called the breast phantom, and it's being compressed between the compression paddle and the breast platform. Let's take a look inside the breast platform. We have the X-ray detector, the ultrasound probe, a layer of mineral oil, and a sheet of plastic called TPX. Humans can hear sounds with frequencies up to 20 kilohertz, but medical ultrasound uses frequencies about 100 times greater than that. And unlike audible sound, it doesn't travel through air. So that was our first challenge, to find a way to connect the ultrasound probe to the breast using a combination of liquids and solids. And that's called acoustic coupling. We solved the acoustic coupling with the mineral oil and the TPX. Why and how we done that is a topic best suited to a series of lectures. So during a mammogram, the X-ray detector and the ultrasound probe move within the breast platform, and that's to acquire an image of the entire breast. The basic principle of ultrasound is that it generates sound waves. So here the ultrasound probe generates sound waves. It travels through the mineral oil, through the TPX, and into the breast. Once inside the breast, when the sound waves hit some internal breast structures, some of the sound waves get reflected back to the probe, which is then listening for the reflections. And the time between when the sound waves are sent to when the sound waves are received is used to create an ultrasound image. Shown here is an image of our very first breast platform. This is the X-ray detector. That's the ultrasound probe. This ultrasound probe was a handheld, off-the-shelf probe. And we got relatively good images with this setup, but the ultrasound probe was only 40 millimeters long, so obviously not long enough to cater for all breast sizes. So that was our next challenge, to find a way to make this ultrasound probe longer. Before I tell you how we went about doing that, I'm going to tell you a bit more about ultrasound systems and how they work. So an ultrasound system is made up of two components, a beamformer and an ultrasound probe. Just to delve a bit deeper, we can have a look at this diagram, and here we see the beamformer and the probe again. So the beamformer is made up of N transmit and receive channels. An ultrasound probe is made up of, so let me just go through back there. That's channel transmit and receive channel 1, channel 2, all the way through to channel N. The probe is made up of N acoustic elements, so there's element 1, element 2, all the way through to element N. During ultrasound imaging, the beamformer generates an electrical signal on the transmit and receive channel, which the acoustic element converts to a sound wave. And like I said earlier, that sound wave hits some structures in the breast tissue, and that gets reflected, and the reflections are detected again by the acoustic element, and it converts it back to an electrical signal, and the beamformer uses that to generate the image. So to return to our challenge of trying to make that probe longer, we could fairly easily add more acoustic elements to the ultrasound probe, which would make it longer. But the limiting factor in this setup is the number of transmit and receive channels available in the beamformer. So that gives us two potential solutions, and that is to either find a way to increase the number of transmit and receive channels or to widen the acoustic elements themselves. Our first attempt was to increase the number of transmit and receive channels, and we did that using a piece of equipment called a multiplexer. The best way to conceptualize a multiplexer is an old switchboard operator who can connect one phone line to many other phone lines. So that's exactly what the multiplexer does. Here it connects all the transmit and receive channels to ultrasound probe 1 or ultrasound probe 2 or all the way through to ultrasound probe N. And what that allows us to do is to put many small ultrasound probes next to one another. So this is that solution realized. This is the probe, and this probe is actually made up of 10 little probes. So there's probe 1, probe 2, probe 3, 4, 5, all the way to probe 10. Everything else that you see in this image is the internals of the breast platform. So this is an image that was acquired with this multiplexer probe, and it's of the breast phantom that we saw earlier. I'm sure that everybody can tell that this image isn't very useful. It has a number of issues. Maybe let me point out firstly. So the breast is sitting in this area. Yeah, that's the breast over there. So I mean, you can see there isn't really anything valuable that you can see inside there. So the issues are that it has the imaging noise, and you can see all this like lines all over the show. It's also lack of clinical information, which I was just talking about now, or the lack of reflections in the breast. And the cause of these issues was the electrical noise and the susceptibility of the multiplexer. Another major issue was because we were using a multiplexer and a single beamformer, we actually needed to acquire 10 images, because there were 10 little probes in the one probe, to acquire one single ultrasound image. And you can kind of see that not so much from where you're standing, but there are 10 bands that have been stitched together here, which is the entire image. And what that means is that it takes 10 times longer to acquire this ultrasound image than what it does with a handheld ultrasound probe. And that's not really a good thing, because the compression paddle applies forces of up to 20 kilograms, and that's literally like putting a suitcase on your breast. So we obviously want to minimize that time. Ultimately, we decided to put the multiplexer aside and consider our second approach of widening the acoustic elements. So this diagram illustrates that concept. Here's an ultrasound probe that has 128 acoustic elements of a certain length. There's another probe also of 128 acoustic elements, and it's significantly longer. And that's because the elements themselves have been widened. So this widening the elements has a number of pros and cons, or it has pros and cons. The positive is that it increases the power of the probe, or the penetration depth that's possible. The negative is that as you widen the acoustic elements, the ultrasound resolution or the image resolution drops. So this image shows this wider element probe that we put together at the start of a clinical exam. And it's worth noting that this probe was longer than the handheld ultrasound probe, but not as long as the multiplexer probe. Also wasn't long enough to image very large breasts. This is an X-ray and an ultrasound image that was acquired during a clinical trial using the wider element probe. And what's truly amazing here is that the X-ray, there's no suspicious lesions visible on the X-ray, but on the ultrasound, there is clearly a cyst present. And you can see that over here. So So this was truly great because it clearly demonstrated the capability of a KATO to improve breast cancer detection. Fortunately, the lesion turned out to be a benign cyst. So that was a really good step forward, but this comparison between the image acquired with the wider element probe and one with the handheld ultrasound probe illustrates another issue which I mentioned earlier, and that's one of poor resolution. You can see that this one is a lot blurrier than the other. So at this point, we'd tried both known solutions to our problem, and none of them really was working for us, so we needed to start getting creative to find another. And what we had come up with was this time to not only make use of multiple ultrasound probes, but to also make use of multiple beamformers. Specifically for our solution, we'd selected 2 probes and 2 beamformers. This is an image of our latest multi-beamformer probe. It's partially assembled. Here are the 2 connectors that go to the independent beamformers. These are the hundreds of wires that are still to be connected to the acoustic elements of the probe. This is another image of the same probe. Again, we have the 2 connectors that go to the beamformers, and this is the fully assembled probe. It looks like one probe, but it's actually made up of 2 individual probes that are butted up next to one another. This is another X-ray and ultrasound image that is acquired in another clinical trial, but this time with the multi-beamformer probe. And the ultrasound image demonstrates that we managed to significantly improve the ultrasound image quality. And at this point, we were getting the level of detail within the breast that was acceptable. The current status of the project is we are now assisting Cape Ray with the certification process. Thank you. I'll now hand over to Heidi.